Now that we've discussed measures of central tendency and we understand how to identify the middle of a distribution, now we're going to move on and talk about how cases fall about or are distributed around that measure of central tendency. We're going to talk about several measures, just like we did for central tendency, that include measurements of dispersion for different kinds of variables, our discrete variables and our continuous variables. So, while measures of central tendency give us a numerical estimate of the location of the center of a distribution, it's also useful to know how the cases or our measurement is distributed around that measure of central tendency. And that's where measures of dispersion come into play. Some people call this spread or variability, and it's also useful to think of this in terms of whether your distribution or your variable is homogeneous or heterogeneous. Homogeneous means not much diversity, very similar, everybody's kind of alike, and heterogeneity means there's a lot of diversity in the kinds of responses to a survey or whatever it is your variable is measuring. This is also a numerical measure, and it's unfortunately one that we tend not to use too frequently in our everyday life. So where we use averages all the time, people tend not to report spread very often. There are some exceptions. For example, if you watch the weather report, they tend to report the next day's weather by giving you maybe a point estimate. It'll be about 80 degrees tomorrow, and then a range of values, probably between 78 and 82 degrees. In newspapers, they do a lot of polling, particularly in election years, and they might report, as the Gallup poll I show here says, that in August of 2013, President Obama's approval rating was 44%, plus or minus 3 percentage points. That's our margin of error. That is to say, we believe that 44 minus 3 and 44 plus 3 establishes a range of highly likely values of President Obama's actual approval rating. We have many different measures of variability or dispersion. They include the variation ratio, the index of diversity, index of qualitative variation, the range, interquartile range, mean deviation, and the variance and the standard deviation. As I go down that list from the top one, the variation ratio, to the bottom one, it reflects our differences in levels of measurement. For example, the variation ratio can be used to discover the center of a distribution for discrete non-orderable variables, but not for quantitative variables. The variance or the standard deviation is specifically for variables that have a quantitative nature to them, where we can measure distances on the number line. So we're going to go through each one of these measures, but remember, they all have the same purpose. The measure that's most frequently used in statistics is the standard deviation, and that's where we'll spend most of our time in the remainder of the class after we've discussed all these different measures. Here's the formula for the variation ratio. The variation ratio is quite an easy measure to calculate and also an easy measure to interpret. The variation ratio is equal to 1 minus the ratio of the frequency of the modal category divided by n. In other words, F sub modal divided by n is the proportion of cases that lie in the modal category, and 1 minus that, therefore, is the proportion of cases that fall outside of the modal category. And for this measure, and all of our measures, we have to think about what it means to have a large value or a small value. In this case, higher values of the variation ratio means that the cases are more spread out across the different kinds of the different categories you have. That is to say, there's more diversity, more heterogeneity, or less heterogeneity. Similarly, small values of the variation ratio imply homogeneity or very little diversity. The nice thing about the variation ratio is that you can use it with data that don't contain a lot of information, and by that I mean quantitative information, and it's pretty easy to interpret. The downside of this measure is that if you're a researcher who develops your own recoding schemes, some people might think that however you recode your variables is a bit arbitrary, and the fact is, if you're not careful, you might subtly change how your categories are defined to provide a particular kind of outcome, to put cases into different categories that could shift the variation ratio around. In that regard, this is not really an objective measure, but it could be seen as a subjective measure. Here's an example of how to calculate the variation ratio. I'm showing here the distribution of race based on the General Social Survey in 2000. You can see that we have three categories, white, black, and other, and that our modal category is the white category with 2,244 individuals. We have a total of 2,817 people, and therefore the proportion of cases in the modal category is 0.8. The proportion of cases outside of the modal category is 1 minus 0.8, or 0.2. You can see when it comes to race, at least in 2000, that we see a fair amount of homogeneity because this number is quite small. Larger numbers indicate heterogeneity, smaller numbers indicate homogeneity. Now, you do have to think about what is the maximum heterogeneity, what is the maximum diversity. If we have these three categories, white, black, and other, then the maximum diversity would be to have about 33 1/3% of the sample being white, 33 1/3 being black, and 33 1/3 being in the other category. That would give us a perfect variation ratio of about 0.67. We observe a value of 0.2, which is obviously smaller than complete diversity, and so therefore we again get a sense that this is a relatively homogeneous distribution. In biology, people tend to be very concerned about ecological diversity, and they've developed a lot of measures that have been adapted by sociologists to measure diversity in communities and other kinds of measures of dispersion based on this notion of diversity. Our first measure is the index of diversity, and this indicates whether two measures, if two cases were selected randomly, the likelihood that they would show up in the same category. Our formula here is D, and it's equal to 1 minus the sum of P sub I squared, where P sub I is equal to the proportion of cases in each category. Like the variation ratio, this is a relatively easy measure to calculate and relatively easy measure to interpret. And also like the variation ratio, you're going to find out that it's useful to think is what's the maximum diversity that we could have, and then how does our actual number compare to that. For this measure, again, higher values of D indicate that the cases are more equally spread across our different categories. That is, larger values of D are indicative of greater diversity or more heterogeneity. On the graphic at the bottom, you can see on the left I have perfect heterogeneity. I have 4 categories, and there my diversity is large, and therefore my value of D is large. On the right-hand side, I have less diversity because most of the cases, the greatest proportion of cases, are piled up in the first category and very few in the remaining 3 categories. So there's a great deal of homogeneity, and I would calculate a small value of the diversity index. Here's the same set of data about race that we saw on the slide before, looking at variation ratio, but this time we're calculating the index of diversity. And so I take my frequencies and I calculate proportions for each category. So 80% of my sample is white, 14% is black, and 0.6% is other. I express these as proportions and square them, and then I do 1 minus that value, and I get an index of diversity of 0.34. Again, it's useful to think of what would maximum diversity be, and you can see at the bottom I've shown that 1 minus 1 over 3 gets us to our maximum diversity. That is, if we had an equal proportion of cases in every category and we had 3 categories, diversity index would be 0.67. You can also calculate the diversity index, and it will vary, kind of a perfect diversity index, based on how many categories you have. If you have 4 or 5 or 6 categories, and you use the formula 1 minus 1 over k to figure out what would perfect heterogeneity look like. Finally, we have the index of qualitative variation, and I'm going to argue that this is really the measure we should use for these qualitative variables that we have if we want to talk about diversity. We're going to calculate the index of diversity first. That's the first step in calculating the IQV, and then we're going to make an adjustment to it, which is the k divided by k minus 1 part of that formula, to give a little bit bigger boost to D for variables with fewer categories. So sometimes we have a variable that maybe has 3 categories like our race variable, and other times we have maybe 5 categories like the GSS marital status variable, and we'd like to compare the diversity of those 2 measures. Well, we know that the perfect heterogeneity varies by the number of categories you have, 3 versus 5. The index of qualitative variation compensates for the different number of categories to produce a measure of dispersion that can be compared regardless of the number of categories. This new statistic will have a minimum value of 0 and a maximum value of 1. Back to our example about race, the first thing we do is calculate the index of diversity, which we already had from the problem before, and we get the value of 0.34, and then we're going to multiply it by 3 divided by 2, or 3 divided by 3 minus 1, and we get our value on diversity in a statistic that ranges from 0 to 1 of 0.51. Leaving behind these non-orderable discrete variables, we can move on to variables that have order in them and that allow us to measure distance, our quantitative variables. Probably the simplest measure out there is the range. Again, it may not be the most useful measure, but it often does tell us something, and it's calculated very simply as the difference between the largest value in your data set for that variable minus the minimum value for that variable. So for example, in the year 2000, looking at the variable age, the oldest person who was surveyed was 89 years old and the youngest person was 18, and therefore the range of age is 71 years. Now, statisticians tend not to like this measure too much, and there's kind of a complicated reason for that, and you have to think about random sampling. You've taken one sample, the general social survey in a particular year, in this case the year 2000. It could be a good sample or a bad sample. Bad meaning it produces statistics that don't really reflect what's going on in the general population. But as we'll discuss later in the course, there's reason to believe that particularly with large samples we'll be able to produce statistics or estimates of parameters that are valid. Some statistics are very consistent and produce similar results across different kinds of samples. They're reliable. The mean is one of those measures, the arithmetic average. The mean I called before a democratic measure because every case in the data set contributes to the production of that statistic. You can see that the range is not a democratic measure. It simply takes the 2 most extreme values and calculates the difference between them and says, that's our measure of dispersion. The trouble with using only 2 cases in any kind of measurement is that it tends to vary from sample to sample. It could produce wildly different estimates of the range of values looking at one sample or another sample or a third sample or the fourth sample. It's not as reliable as our democratic measures. On the other hand, it does give us a sense of where do we begin and where do we end, and how cases are distributed around that middle point. It turns out that this notion of reliability is really important to us. And by taking the 2 most extreme cases, the 2 cases that are least likely to occur reliably from sample to sample, the range is really not a very good estimator. But what we can do is we can move in from those extreme points more towards the middle of the distribution and again calculate a range based on simply 2 cases. But this time we're going to calculate the range as the difference between the value of the 3rd quartile and the 1st quartile, and we call that the interquartile range. The interquartile range tells us the range of values within which half of the distribution, the middle half of the distribution, lie. In a sense, this is a better measure than our range because it's based on less extreme values, so it's more reliable from sample to sample. It moves more towards the middle of the distribution, at least as measured by the median, and so therefore it's back to that notion of what dispersion means, which is finding, after we find the numerical center of the distribution, how do cases fall around the middle. So this statistic is more reliable or more stable across samples, and so we like that. On the other hand, it still has this issue that you're basically ignoring all but 2 values in your data set. You're ignoring what's going on in the tails and even what's going on between these 2 values, even though it's more reliable. In the 2000 General Social Survey, looking at the variable age, I've calculated the third and first quartiles. Remember, that's also equal to the 75th and 25th percentiles. The third quartile is 57 years old, the first quartile is 32 years old, and the distance or range between those two values is 25 years. That means that half of the people in the year 2000 GSS were within 25 years of the average age, the median age. We can do a little better and get rid of this notion of an undemocratic or an anti-democratic measure and move on to one that is more democratic and uses all of the data in our data set. The next measure we're going to look at is called the mean deviation. This is taught in a lot of statistics class, but honestly, it's not used in practice. Part of the problem is if you look at the formula, we need to take absolute values. When we move on to other topics in statistics, particularly things like analysis of variance and regression, we're going to want to look at deviations of cases from means, but it's very difficult algebraically to work with absolute values. So we're going to do something else. We'll take these deviations and square them. And that's what we're going to end up doing with this too. But I just want to show you this measure so you get the concept behind how the standard deviation and variance works. Here's what we're going to do. We're going to calculate the mean of some variable. That's y bar. From each case, we'll go to case number 1 and we'll subtract the mean from that case. If the first case has a value on y that's less than the mean, then obviously the observation value minus the mean will be negative. If the first case has a value that's greater than the mean, then when we subtract the mean from that observation, we'll get a positive value. We're going to take the absolute value so that all of the deviations are positive. Now, what that's going to do for us, it's going to say that if a case is, say, 2 units below the mean, the deviation is minus 2, and another case is 2 units above the mean, so their deviation is plus 2, we're going to ignore the sign or the direction and say both of these cases are 2 units from the middle of the distribution. Notice that unlike the interquartile range, which is centered around the median, this measure is centered around the mean. And we're going to calculate this deviation for every observation in our data set until we run out of observations, and then we're going to add up all those deviations. You can see in the extreme that if every case had exactly the same value, then the average would be the same, and the numerator would be 0, and we'd have a value that's very small indicating perfect homogeneity. On the other hand, as cases fall away from the mean, indicating greater heterogeneity, this measure of the mean deviation will get larger. Last thing about this particular measurement, we're dividing by n, so we're really taking an average of these deviations. This makes us even a little bit better measure because if we didn't divide by n, then the values we get for the mean deviation would depend partially on how big our samples were. That is, if we calculate lots of deviations from a very large sample, well, we'd expect the mean deviation to be larger than if we had a small sample where we summed up very few deviations. We'd like to be able to compare measures across samples of different sizes, and we can do that with this measure by averaging it out by dividing by n. So the advantage of this measure, it's a democratic measure and it's centered around the mean. It can also be interpreted pretty easily. The downside of this measure is when we go on to more advanced statistics, we can't use these absolute values and need to do something else. And that something else is to calculate either the variance or the standard deviation, and that's what we're going to look at next. For quantitative data, the standard deviation is the most widely used measurement. In the General Social Survey, the standard deviation of age is equal to 17.4. Unfortunately, the standard deviation is a little difficult to interpret, but let's look at our advantages and disadvantages here. Like the mean deviation, the standard deviation uses all of the cases available to you, and so it's what I call a democratic measure. Also, while it will take some work to understand what normal distributions provide for us statistically, once you understand normal distributions, in particular the Gaussian normal distribution, this statistic can be easily interpreted. Until we get through the information and the lectures on normal distributions, however, I suspect that interpreting this variable will go to the disadvantage column, that this is a little bit difficult to interpret. And then finally, the statistic is in the right direction. That is, small values of the statistic indicate little dispersion, little diversity, and large values of the statistic indicate a lot of diversity or heterogeneity. What are the disadvantages of this particular measure? Well, you can see that instead of taking the absolute value in the numerator, we're squaring things. What that means is, as cases are further away from the mean, as our deviations get larger, and then we square those differences, even though this is a democratic measure where every case participates, cases that are in the tails of the distribution count a little bit more. In fact, the further away they are from the mean, the more they count. Finally, we have to take the square root of this whole thing so that we can bring it back to the original metric. We tend not to report the squared values. We take the standard deviation. So let's look at this slide for a second. Under the column labeled samples, you'll notice I'm providing the standard deviation and the variance, and you'll notice that they're identical. We have s squared sub y, which is the variance of some variable y, which is the sum of y minus y bar squared divided by n minus 1. The only difference between these two measures, and the one above it, the standard deviation, is the radical sign, or taking the square root. People report variances, and they also report standard deviations, but I think it's a pretty good practice to always report the standard deviations. Thinking about that age example, we calculated the standard deviation of age to be about 17.1 years, and we could report the variance, which is 17.1 squared, but who thinks of things like age in terms of squared age? It doesn't make sense for interpretation or for understanding, so we should always return our statistic to its original metric. Now let's move over to the other column labeled populations. Here are the same two statistics, the standard deviation and the variance, calculated for populations. Notice that the formulas are very similar. If we look at the variance, it's simply the sum of y minus mu sub y squared divided by n. So the variance here, again, doesn't have the radical sign. The standard deviation, on the other hand, is the same value, but with the radical sign. So again, the difference is simply whether we take the square root or not. If we compare across the columns, you'll notice that in the denominator, we're using either n for populations or n minus 1. And that gets a little confusing. We're not going to cover it thoroughly in this class, but it turns out that when we calculate standard deviation or variance from samples, our estimates tend to be, they have the potential for bias in them, and that's something we don't like in our statistics. We prefer statistics that are unbiased estimators of populations. Keep in mind what we're doing here. We're taking a sample, that's what we typically do, calculating a statistic, say the standard deviation, and we would like to produce an unbiased estimate of the population parameter. We believe that S sub y is a good estimate of sigma sub y, but if it has a bias to it, it's a little bit of a problem. Dividing by n minus 1, which is also known as the degrees of freedom, reduces that bias. That's the only reason we divide by n minus 1 versus n, and here's a simple way to keep it straight. When you do your own work, you probably won't use populations. You'll probably use data like the General Social Survey. And anytime you use data that are a sample taken from a larger population, you want to make certain that you divide by n minus 1 and not n. I'll give you one more caveat about that. If you have a very large sample, like the General Social Survey, maybe you have 1,200 cases, does it really matter if you divide by 1,200, n, or 1,200 minus 1, n minus 1? And the answer is that denominator is so large anyways that a difference of 1 is almost undetectable. On the other hand, if you had a population of 6 versus a sample of 6, dividing by 6 or dividing by 5 introduces a pretty large difference. So this correction is really important for small samples and way less important for large samples. But Don't ignore it. Anytime we're working with sample standard deviation, divide by n minus 1 or the degrees of freedom. Anytime you're working with a population, divide by n. Let's put together all of our measures of central tendency and all of our measures of dispersion. I've calculated the mean age from the 2000 General Social Survey. It's 46 years old. I've calculated the median age as 43 years old. We can see here that the mean is pulled towards the tail. This distribution is skewed to the right, skewed towards older respondents. We know that the average is affected by extreme values in a way that the median is not, and so our mean is pulled towards those older people, and we observe a little gap between median age and mean age. We also find the modal age of 32. I want to point out that when we look at that column for the 32-year-olds, just like we saw before, that when we calculate the mode, well, is it really 32 or is it a little bit closer to 40? There's lots of those columns that are almost as tall as that 32-year-old column, which is technically the mode. But this is really a multimodal distribution, and our mode is not our best measure. Our range goes from the column on the far left to the column on the far right, and that's equal to 71 years. Our interquartile range is 25 years. That is the middle 50% of the distribution centered around the median, and that's that shaded dark area in the middle. That's the concentration or a measure of dispersion around the median. And finally, we have those three dashed lines. The line in the middle is the mean age, 46 years. The two lines are +1 standard deviation, so the mean plus 17.4 years on the right, and the mean minus 17.4 years on the left. Now, when you go produce a statistic, it's unlikely that you will produce all three measures of centrality or central tendency and all of these measures of dispersion. But I put them together in one graphic to show you that they give us a different view of the data. Which one you select will depend on the purpose of your reporting, what it is you're trying to accomplish, and the story you're trying to tell. You can also calculate variability around a dichotomous variable. And it's pretty easy. We just need to know the proportion of cases in one category and the proportion of cases in the other. So here we can get our variance as equal to the proportion coded 0 times the proportion coded 1. Remember, we have to take the square root of that to get to the standard deviation. So in 2008, we observe approximately 40% of the sample believing that marijuana should be legal, and approximately 60% believing that marijuana should not be legal. We express these as proportions, 0.3978 and 0.6022. We multiply the two proportions together and get a variance of 0.24. Returning it to its original metric, the 0,1 metric, we take the square root and get a standard deviation of 0.49. Now, we have to compare this to maximum variability. When we only have two categories, legal and not legal, the most variability we can have is 0.5, a 50-50 split. And we're observing very close to that, this 0.49. Skewness is another measure that's a numerical value that gives us an indication of how symmetrical our distribution is. If a distribution of numbers is symmetrical, then the median and the mean are probably going to be equal to each other. We're going to take advantage of the fact that when we have skewed distributions, the mean is pulled towards the tail of that distribution, and it's going to allow us to calculate for a particular variable the difference between the mean and the median. Well, if the difference is 0, then we believe that distribution is symmetrical. As that difference gets larger, we have reason to believe that the distribution is skewed. So the formula shows us that our skewness is going to be 3 times the quantity y bar minus the median divided by the standard deviation of y. When this value is small, or 0, no skew. When this variable is negative, it has a tail to the left of the median, and when this value is positive, it has a tail to the right side of the median. Let's look at calculating an example. In 2008, General Social Survey respondents were asked, what do you think is the ideal number of children for a family to have? We observe a mean value of 2.49 children and a median value of 2. We have a standard deviation of 0.88, and therefore 3 times the difference between the mean and the median divided by the standard deviation is 0.167. Because this value is positive, it says there's a tail going off towards those larger numbers, the 3, the 4, the 5, and the 7, and so forth. You can see that the mean from the graphic is pulled towards that tail, and the median is lower than it. If the distribution had been symmetrical, falling off equally on both sides of the mean and the median, then the difference would be approximately 0, and so would the skewness. We're going to have other videos that discuss in great detail normal distributions and how to use them to interpret standard deviations. But I'm going to give you some guidelines now to help you with your homework and understanding in the class. There's something I call the empirical rule, and you can use this anytime you have normal shaped distributions. First part of this empirical rule is that in a symmetrical distribution, a distribution that looks to be bell-shaped and approximately normal, you will have about 68% of all your cases within one standard deviation of the mean. That is, when you find the mean of a distribution, if you moved one standard deviation above the mean, you'll have about 34% of the distribution there. And if you moved one standard deviation below the mean, you'd have about 34% of the distribution there. So taken in total, the mean plus or minus one standard deviation would capture about 68% of the cases. In this same normal distribution, if you moved out 2 standard deviations, the mean plus or minus 2 standard deviations, you'll capture or cover approximately 95% of the distribution. That is to say, if I go from 0 to 1 to 2, those are my standard deviation units, I'm covering 0.341 and then additional 0.136 of the distribution. And of course, I'm doing the same thing on the negative side or below 0 and adding up 0.136, 0.341, 0.341, and 0.136. I get approximately 95% of all the cases. Finally, if we pushed on a little further and looked at plus or minus 3 standard deviations from the mean, the empirical rule tells us that we capture, in essence or essentially, all of the distribution. In a normal distribution, almost all the cases will be within 3 standard deviations of the mean. What if our distribution isn't normally distributed? Doesn't look like a normal distribution? How do we interpret the standard deviation then? Well, we can apply Chebyshev's rule. Chebyshev's rule applies really regardless of the shape of the distribution, but I tend to use the empirical rule if a distribution looks normal and Chebyshev's rule otherwise. So here's Chebyshev's rule. First of all, we have to acknowledge that it's possible, depending upon the shape of the distribution, that very few cases fall within one standard deviation of the mean, plus or minus 1s. We should find at least 75% of all the cases within 2 standard deviations of the means. That is, 3/4 of all the cases should fall plus or minus 2s. And we should find at least 8/9 of all the cases within 3 standard deviations of the mean. Again, as we move from the middle of the distribution, regardless of its shape, towards the tails of the distribution, we encompass a greater proportion of cases. And we can generalize Chebyshev's rule as we should find at least 1 minus the ratio of 1 over k squared cases, proportion of cases, falling within k standard deviations, where k is any number greater than 1. We can put together a nice visualization, and I really encourage you, if you end up doing any statistics, that besides just producing things like means and standard deviations, that you find a way to visualize the information. People really understand better by looking at the pictures, and for some things like, how do we know whether to use Chebyshev's or the empirical rule, you have to look at a frequency distribution to determine which of those to use. So I'm a proponent of visualizing information, and we're going to show you one visualization here. And if you pause the video and look at the bottom, you can find 2 different links that will take you to websites that talk about how to produce these box and whisker plots. Box and whisker plots are typically not used for a single variable. They're used for comparing values of a variable across categories. So in this top graphic, I'm showing you 2 distributions of sexual frequency for men, one for men and one for women. Now we have this box, and we have to understand what the box and the different pieces are. Inside the box, the middle line of each box represents the median value. We can see here that median sexual frequency for men and women are virtually identical. Those 2 lines are at the same value, which appears to be greater than 25 and less than 50. A little tough to tell from the scale over there. The box itself represents the middle 50% of the distribution. That is, the distance from the bottom of the box to the top of the box encompasses the middle 50% of the distribution. So the box shows us a measure of central tendency, the median, its location within the box, and then the range of the box itself shows us the interquartile range. The box on the right for the women is kind of squashed down. That is, when we look at sexual frequency for women, women are more homogeneous than men with regard to the middle 50% of the distribution. Why? They have a smaller range of outcome values than the men, who have a larger range of outcome values. Now we're going to put some whiskers on this. The whiskers are those lines extending vertically from the bottom of the box, at least for the men, there's a very tiny one, and the top of the box for both the men and the women. This line extends no more than 1.5 times the interquartile range. So once we establish the interquartile range, we multiply it by 1.5, and we extend the whisker out until we get to the first case up to but not including the case that exceeds 1.5 times the interquartile range. This shows us whether there's a tail to the distribution, and both of these distributions for men and for women exhibit such a tail. The tail for the men is longer and indicating more extreme values. Finally, we can plot what are called extreme values, and they're little points. They're a little hard to see in this graphic, and they are the points that are beyond 1.5 times the IQR, and typically we only plot cases that are 3 times the interquartile range, and we call them extreme outliers. The graph at the bottom is a similar kind of graph. I've tilted it on its side. I prefer when they're tilted on their side myself because it looks more like the frequency distribution. And here I'm looking at a measurement of word sum, which is a variable. It's a variable that has outcome values that range from 0 to 10, and it's a vocabulary test. Taking the vocabulary test, you might score 0, none of the words correct, or you might score 10, all of the words correct. And I've broken this out by 3 different categories: people who identify themselves as being conservative, people who identify as being moderate, and people who identify as being liberal. Well, let's look at these 3 distributions. You can see that the median for moderates and conservatives are identical, 6 words. And yet the variability for conservatives is greater than the variability for the moderates. The moderates, that the middle 50%, the interquartile range, goes from 5 to 7. The interquartile range for conservatives goes from 5 to 8. So the conservatives are more diverse with regard to this word sum variable compared to the moderates. You can see that the liberals have the same interquartile range as the conservatives, so the middle 50% lies between 5 and 8 for liberals as it does for conservatives, but that the median is higher. Median word sum for conservatives is 6, while it's 7 for liberals. And then finally, you can see that the tails are pretty much the same for the liberals and conservatives, and it's skewed to the left, while the moderates tend not to have an extreme skew to the left. I hope you enjoy this cartoon at the bottom, and I definitely don't recommend that you sit with your boyfriend or your girlfriend and draw box and whisker plots to describe your relationship. As usual, if you have any questions, please feel free to contact us, and we'll do our best to answer all of them.